Okay, good morning. Let's have a class. First of all, we go through the half of the first lecture slides. And this is what I usually do. You will see underneath the first section, I put a link of the YouTube channel. So that is directly coming from the recording of the classroom. So if you're missing something, and you could go back to review. Okay, and some people are not come to the lecture in person, then you can watch online. So it's up to you. Just want to let you know. Every time I will do that. At the same time is also the lab. I'm going to show you. For example, the lab section. I also had first microscope use underneath here. So if you occasionally miss lab, you can go back to watch. But this is usually is a 9:30 lab because I'm not going to recording every single piece. It's the same thing. Okay. I just want to remind you, it says what we do. Lots of people said very helpful, and especially during the review, and they're really helpful them. So that's why I keep doing since the pandemic. And during the pandemic, we're required to do it. But afterwards, I think it's a very good strategy to engage you learning. That's why I keep doing that all the time. Okay, so let's continue to talk about history. We talk about the Louis Pasteur, the swan neck flask, and then we're going to go to a next very important microbiologist in the world, in the history, which is a German scientist, Bob Koch. So I'll just say Bob Koch. He did lots of the good things and the milestones for the microbiology, but the most important thing here related to the microorganism and the disease and the subject is a very important concept. We call it a Koch postulate. And this Koch postulate in these slides explained very well. But it looks like it's tedious. So we can use a very simple language to understand it. So first of all, for any of the pathogen, if healthy people absence, which means no pathogen, sick people present. So let's say tuberculosis. If the people or the mice who got tuberculosis, then the tuberculosis will certainly exist in the lung area of the people or the mice. And if you're healthy people, then the tuberculosis will not be there. So that's very simple. Healthy, absence, sick, present. The second thing, okay, the same pathogen can be isolated from sick, I just say subject, to form single colony. This is a very important concept, and you can read here corresponding to the one called pure culture. So if I have a tuberculosis, then I get isolated, and then I could get a pure culture. Okay, that's very important. We could isolate and get it from a pure culture. A pure culture is a single colony, and we'll explain that to you later on. Then the isolation, infected, or we say contaminated, a healthy people, a healthy person, same disease, same results, or we say same disease. So let's say I get a pure culture of tuberculosis, mycobacterial tuberculosis. Then I infected it, or I artificially inoculated it into a healthy mice or guinea pig. then the same disease, there will be the outcomes, which means they also will got tuberculosis. Last thing is very important, re-isolation, which means from the thick subject, the pure culture of the tuberculosis can be re-isolated, still forming pure culture. So if you want to say using layman language or non-technical terminologies, languages, to explain the Koch postulate is something like this. The healthy people, no pathogen. Sick people, you got pathogen. The same pathogen you could get a pure culture, then infected or inoculated a healthy subject, the same disease. Finally, the pure culture can be re-isolated from the sick person. So this is a very interesting and a very important theory. Talk about the relationship between microorganism and the infectious disease. But there is something I want to add to that. Why microbacterial tuberculosis is a subject by Bob Koch. You pretty much know or you heard about something. This is called TB. Long time ago, is 150 years ago, or even 100 years ago, or even 70 years ago. This is equals to lung cancer. So by the time people who got TB, there is no way to do any treatments until the antibiotics comes out. The antibiotics comes out is back 1950s to 1960s. But then they have a problem because we're using too much of the antibiotics, so it becomes antibiotic resistant. Then today you have a multi-antibiotic resistant TB comes out. So that's another story. So why microbacterial tuberculosis is a subject? The reason is that. And we will mention this in our lab. We're not going to do a practice. This bacteria is very special. We need to do a very special stain called acid-fast stain because their structure a little bit special. We'll talk this next week. The second thing, when you read through the Koch postulate, you will find something is not really true recently or in the modern area. For example, the first one. The microorganism must be present in every case of the disease but absent from the healthy organisms. Does that true? How about the asymptom people? Is that right? During the COVID-19 area, we have lots of people tested negative or tested positive but without any symptoms. So, that something is missed points by the Bob Koch. But it is not his fault because by the time the immunology has not been developed. So there's no science for immunology yet. That's very late, like 1950s. When the modern biotechnology or molecular technology developed, then people get to know about immunology. So these are some things we want to mention about that. Another thing is the guinea pig. Looks like a mice. It's not a mice, it's a pig. That's a very important experimental tool because lots of the characteristics, the physiology characteristics, very similar to the human being. So that's a guinea pig used in the medical area a lot. Okay, so this is something I want to talk about. Okay, the pure culture. This is the key. How we get the pure culture? Because the pure culture indicating one genome name, one species name of a bacteria or microorganism. So how to get a pure culture is a challenge. In the history, there is a debate about it, how we're going to get it. There is a competition between the two major groups, is Louis Pasteur and the Bob Koch. They are not really friends, they are the competitors. And I want to make sure the spelling is correct. PSTEU, oh, okay. So, how are you going to get a pure culture? There is two groups, they're going to debate about it. How are we going to do it? Louis Pasteur's group, by the time, they think using liquid medium, which is bacterial broth. Okay, I have a tube, a bacterial broth. I'm growing E. coli, 35 degrees Celsius, 24 hours. This tube will become turbidity. Lots of bacteria are going to be there. How many are there? 10 to the power of the 8 cells per ml. Very density. What do you mean the pure culture? The pure culture means one single E. coli cell. Louis Pasteur said we can using liquid media. How he do? This is what you do in your chemistry lab a lot. You may don't like it, but you have to do. He prepared multiple dilution tubes. So for example, we prepare 9.0 ml nutrient buffered broth. This is 9.0 ml, 9.0 ml, 9.0 ml. Then we're going to add 1.0 ml into the first one. Then this is diluted by 10 to the first, 10 to the power of 2, 10 to the power of 3, 10 to the power of 4. Then he think use this method. Okay, repeatedly you do. At the end, you could get to 1 cell. Can we do that? Theoretically, yes. Practically, no. Because we cannot verify that the final tube is exactly only 1 cell there. How about 5 cells there? How about 6 cells there? But that's a good technology. Okay, that's a dilution scale technology which has gave the people lots of the inputs. And later on, they used to isolation, enumeration bacteria, and the cultivation bacteria. So certainly, liquid media is not a good idea. So Bob Koch's group think about it. We have to use solid media. So what is solid media? And by the time when you're using a solid media, you need to choosing the material, and it's very challenging. Why? The material you have to cultivation bacteria. The bacteria has to grow, which means. But the bacteria cannot eat it. So he tried lots of the material. At the beginning, there were lots of the holes there. The bacteria couldn't eat it, or maybe broke it. This is the first challenge. The second challenge, the material has to be solidified at room temperature. But they also have to be melted at a heated temperature. So that's because you have to prepare it. So that's another challenge, which the material you're going to be. So his group tried a lot of the materials. The very close to is jelly. So it's like a fruits jelly. You can buy a bottle from the Kruger and put on your sandwich with the bread. It's very close because it's soft, it's a solidified material. However, it's still movable and the bacteria could use it. But the nutrition of the jelly is huge. Bacteria can use it. But it's failed. So what happens? By the time there is one person who is working, is water, is Dr. Water Hessen. It's a German scientist, is Dr. Koch's postdoc. Okay? By the time he's working there, he's spending lots of time. In a very hot summer Sunday, around, I would say around back to 1920s-ish, or even like, I would just say 1900s. a very summer day in the German. There's no air conditioning and maybe a little bit of fan. He's still doing the research. So his wife, which is Fanny Hesse, that's Fanny Hesse, he said, honey, it's a time for the lunch. And today I prepare pudding. So what does the pudding looks like? It's an agar, is that right? It's like a jelly, like an agar. It's more solidified than the jelly. Then Dr. Walter Hesse said, okay, pudding, that's a good material. Then he go back to make using the material from the pudding to make the agar. And finally, it's successful. Because why? Agar can let the bacteria grow. Bacteria will not block it. Agar is solidified at room temperature around 25 to 40 degrees Celsius, but melted more than 55 degrees Celsius. It's very easy to do the preparation. And the people want to remember Fanny Hesse, and Fanny Hesse later on has made a big chapter of the modern microbiology history. And she also joined the Dr. Koch's, Robert Koch's group and become a research associate there. So there is some story behind it. Now, another thing is that once you have agar generated, okay, we need a container. The container, in the old time, people use a rectangle one. But the rectangle one, you know that it's not going to save the material because the same parameters, it's going to be the small area. So we have to use a circle one. Who find that? Richard Petri. That's why today you will see in the lab for those agar plates, empty agar plates could be made by glass or by plastic. We call Petri dish. That is the reason we call it Petri dish. Okay? That's very important for the pure culture. Okay, now how are we going to get to pure culture? This is the one we will practice in the lab. It is very important how we're going to do it. We cannot use liquid media. We have to use solid media. So how we do it? It's agar plates. Okay, I have a bacteria growing here. Bacteria liquid. Very turbidity. I have to use a loop. It could be a metal loop or a plastic loop. It depends on the lab. The loop, I'm going to pick the bacteria. In this first corner, I will do a very intensive streak. The first culture is very intensive. Then I have to flame the loop, which means you change a new loop or you burning the loop on the Bunsen burner to kill the bacteria. Then on the side of the first culture, you do a second, less intensive streak. Then you're going to change the loop again. Using another new loop or sterilize it, put on the Bunsen burner from the edge of the second one, do a third one. Less intensive. Sometimes people think it's not enough, so they do the fourth one. Will be like that. Okay. Then this agar, you need to add 35 degrees Celsius, growing 48 hours. What you gonna see? After that, you will see lots of the dots there. Lots of the dots will be like that. They will be very messy here, but the dots showed up. These are called a colony. This is called a colony, which means a group of bacterial cells coming from one mother cell representing one genome name and one species name. We call this is a pure culture. And everything further down, some of you working with professor in a health science center at WVU, you're going to do a genotyping of this one, do the sequencing. You all have to come in from that pure culture. Because that means one genome name, one species name. If it's E. coli, it's only E. coli. If it's Salmonella, it's only Salmonella. If it's Listeria, it's only Listeria. If it's mixed, you got a different genomic information. It's very important. This is the technology we will practice in the lab. It's called stream plating. That is one important technology, same as you use microscope. So we will do a couple of times in the lab, okay? So that's Bob Koch finally create these methods, and exactly what he show you on the slides is the strip plating methods. The slides only did 3 course, but we could certainly do 4 or 5, okay? And you will see finally, after incubation, you see the colony there. And you see the different color. One is red, another one is like a little bit of pink, a little bit yellow. Certainly, there are 2 different types of the bacteria there. Okay, certainly there are 2. But I want to also cautious, even if these colony or the same colors and same morphology, you could not just say they are the same bacteria because it looks the same, but the genomic information may be different. Okay, so this is the first insights, what we see, the bacteria on the agar plates. Now, what is the agar, by the way? Polysaccharides from seaweed. So what's the materials of agar? It's not really pudding later on, okay? It's not really as a pudding what you're eating today. It is a polysaccharides. It's a sugar. You know that? Monosaccharides, disaccharides, polysaccharides is sugar. Polysaccharides from seaweed. This is the material people are using later on. Okay? But keep in mind why this is important, because solidification, melted, cultivation bacteria can grow. So, in the lab, you always remember, agar will not be broken by the bacteria. It's only broken because you didn't do it carefully. Okay? So that's something we want to talk about. So this is the one, explain what is the agar, what's the components of the agar. It can be remain solidified over a very wide temperature range. Okay. Last one of these slides we will talk about is a name system of a bacteria. I have something addition to the slides. We will talk about that. So the name system is very similar to lots of the others. It's called a binomial nomenclature. So binomial system. I just say binomial system. Okay, it's easy. So what this means? Okay, let's say E. coli. Full name is Escherichia coli. Escherichia, this is coming from a Japanese scientist. He is the first person to find it. So Escherichia. Then coli. Coli is which means it's a loss. This has to be italic. Okay, I can do it. So not normal, have to be italic. Escherichia. This is the genome name. And coli, this means species name. And in order to help you understanding, we also using acronym. So we can write E. coli. Okay, so for example, Listeria monocytogenes. It's a pathogen we will mention all the time, causing the foodborne issue in the United States. The genus name or genus name is Listeria. The species name is monocytogenes. This have to write italic. Okay. However, we also could write L dot monocytogenes. But there is one exception I want to mention is Salmonella. Okay, this is a very special one. Salmonella is a pathogen we mentioned in the poultry. So, for example, Salmonella Thompson. Salmonella Thompson. Salmonella is italic. So Thompson should write in non-italic. Why? It's very special. Salmonella and the other pathogen are a little bit different, although it's a commonly recognized foodborne pathogen. The pathogen, what we recognize for Salmonella, is one of those subspecies. The full name of Salmonella Thompson should be Salmonella enterica, subspecies enterica, and Thompson. All these sections has to be italic. This is non-italic. And people think this is too long. And people also think all of us are smart enough. So they skip this. There are lots of things happen in the microbiology area. They think you are very smart, so they skip this. But it's going to confusing you. So if we connect these together, that is italic, that is not italic. So the simple answer, why Salmonella Thompson? The Salmonella is italic, the Thompson is non-italic, because Thompson is subspecies name. It's a subspecies name. You don't have to do it. So whenever you read a book, read a manuscript, a publications, when you see Salmonella Thompson, somebody using the Thompson is italic, they're wrong. Now another example will be Salmonella typhimurium. That's lots of people will mention. The typhimurium, lots of people still write like italic. That's wrong. That should be the normal. Okay, because it's a subspecies name. Here are some of the examples. Bacillus arthritis. This is Bacillus will cause the endospore we're going to do in the lab for the endospore staining. Clostridium botulinum. Clostridium botulinum will cause there's a food botulism, infant botulism, woods botulism. We'll mention our exams too. E. coli we'll mention all the time. We use all the time in the lab. Streptococcus pyogenes. This is one is called strep's rot. We will mention detail in the exam too. Okay, so this is something briefly we mentioned about that. Okay, this end up with our first slides. So we're going to finish it, then we're going to go to the second slides. Second slides, we basically talk about microscope and the staining technology. This is very good. I think we talk about the slides too this week, and next week will be very well aligned with our lab work. Because our lab, today we do simple stain. Next week, Tuesday, we do the gram stain. Thursday, we do endospore stain. And then we have unknown practice for gram stain, which is completely followed what we talk about in the lecture. So, which means we talk about here, but we also let you practice in the lab. Okay. So, this is the second lecture. Exam 1, lecture 2 is microscope and staining technology. Here is the thing. Microscope basically have two different categories, which is light and electron microscope. This is our first slide, tells you very briefly. Because of the energy resource. So energy resource could be separated into light microscope and electron microscope. Light microscope has 5 Ds, including bright field. This is what we did in the lab. We already talked detail in the lab 1. Dark field. We will talk briefly, very quick. Fluorescence. Phase contrast. And laser confocal microscope. Laser confocal. Bright field microscope, dark field fluorescence microscope, even phase contrast is normally in the lab. It's not very expensive. Laser confocal microscope is a big piece. Somehow between $150,000 to $350,000. As a faculty, we will need a special permission from the university and apply a grant, equipment grant to have it. You cannot just walk in and say that, can I buy laser confocal microscope? It's really advanced tool. Okay, so this is a light microscope. If the energy resource is electron, then we will have an electron microscope. Basically is 2, scanning electron microscope, and another one we call it a transmission electron microscope. What's the difference between that? Transmission, since it's called transmission, you can see the internal structure. Scanning basically is on the surface. You could see 3D images. Electron microscope at WVU, only the shared facility, the building behind the Evansdale Library has it. It's a big piece of equipment. You need a training, the certification, and the permission to use it. It's not like you just walk in and say, I want to see the results on under the electron microscope. So just want to let you know. Our thing in the lab is only this small piece right here. Okay? So that's some opening remarks we want to explain to you. Resolution. Remember this guy? RP equals lambda divided by 2NA. It's called the resolution power. The lambda is wavelength of light, NA numerical aperture. And we say what means RP? The resolution power is a capability to differentiate or resolve the two closely attached particles. That is what it is. Okay? Then you read this sentence. Wavelength of light used is a major factor in resolution. Shorter wavelength equals greater resolution because of this formula. Remember, this number, the smaller, the better. Which means better resolution capability. How do you know it's smaller? 2 is fixed. Numerical aperture is fixed. You can only do is this wavelength. Therefore, the wavelength has to be the smaller, the better. And we mentioned in the lab, the wavelength of a bright field microscope, 650 nanometer. Electron microscope, the wavelength is much shorter than that. Okay, just want to let you know. That's a conclusion. But where it comes from? It comes from that equation we talk about in the lab. Resolution light and electron microscope, you can see the difference. Electron microscope and the light microscope, you see the difference. Okay, this is a bright field microscope. We already talked about everything. So we skip and very briefly. Remember, all these things you should know: total, magnification. We talk about working distance. Just very briefly in your mind, you can go over it. We talk about the resolution power, we talk about the parafocal, and we talk about a very important thing is oil immersion. So these we already did in the lab, so we're not going to spend a bunch of time here, okay? Structure of a microscope, it's more detailed, but the major structure we already introduced you in the lab. Oil immersion. Now this is the slides is better explained to you. You have a glass, you have air, you have a glass again, you cause refraction. And the oil, the refraction index, is similar to the glass. So we put 1 drop of the oil, we will be eliminate, or we say decrease the reflection. Okay, so that's oil immersion. Okay, next one, we want to talk about dark field microscope. This is something, is an important tool in the microbiology area, dark field microscope. So what is that? When you see the slides, it's a little bit confusing you sometimes. Okay, let's just draw a brief microscope picture. Objective lens, a stage, and you have a light resource right here, and then you have a condenser. Okay, condenser is right here. We just draw a couple of things. Okay, normally, a bright field microscope, the light is go this way, it go this way, it go this way, just like this. Dark field microscope are very special. Is underneath the condenser. There is a solid block. A solid block. So, the light going through the objective lens is perpendicular. It will become this, become that. This angle is 90 degrees, perpendicular. Therefore, what happened? Indifferent from light field, bright field microscope, dark field microscope, the background is dark. Like you see it. And then your sample is showed up. Because of the solid block underneath the condenser, the light going through objective lens is perpendicular. It's a very magic stuff. It's a very smart one. Why? In the clinical area, dark field microscope have a big contribution for 3 special bacteria. The 3 special bacteria we call spiral sheet. The spiral sheet looks like this. That's called the asexual filaments. And very soft, easily to be damaged with heat. So you cannot use traditional staining technology because with heat fixing, it will be melted. That's for special bacteria called spiral sheets. What are the examples? There is 3 major pathogens for spiral sheets for the human being. And you heard about these. Treponema pallidum. What is this called? Syphilis. This is #1 sexual transmitted disease in the world. Trypanemma palladium is a spiral sheets. What's the second one? Bulla, Rela, Burgdorferi. What's that? Lyme disease. You heard about this one? Absolutely. Is in the arm, you will have a target rash, a red target rash. In the Connecticut, like this, target rash. This happened in the Lyme County in Connecticut. That's why it's called a Lyme disease. Borrelia burgdorferi. The next one, leptospiral interrogant. This will cause your eyes become yellow. We call it's called John Dines. It's related to some of the liver damage disease, but not really sometimes. These are the 3 spiral sheets. We use dark field microscope can do the observation. Trypanemma palladium is right here. Look at the asexual filaments. And the Borrelia burgdorferi, I don't have it right now. Last slides, can you see? Leptospiral interrogans. And the leptospiral interrogans is very special. We call it a hook shape. So, if some people have a yellow eyes, they go to see a doctor, have vomiting, diarrhea. Underneath dark field microscope, you see the hook shape like that. It's spiral sheets. It's leptospiral interrogans. It's a very quick diagnostic. That's a picture really good. Look at that. There's a downstairs. Okay, so at the bottom, that's really good. Okay, so that is what we call for dark field microscope. Okay, the next one, phase contrast microscope. This guy, we will talk a little bit of physics, but not going to be too much. So phase contrast microscope. Okay, so there are the 2 things you need to know. The light is going through this, transfer to the wavelengths, okay? Okay, that's a peak, and then you have a bottom. Okay, you have a bottom like that. Okay. Now, the basic physics is that for the light wavelengths, if you have a 2 peak overlap with each other, it will become very bright. If you have a 1 peak, and then you have another one goes the opposite direction, it will contradict with each other, it's going to become dark. So, let's say I have this condenser, I have this objective lenses right here. Okay, this is the energy resource. I go this way. Normally, you're not going to see anything because you have 2 wavelengths from the specimen. One is on the peak, and the other one is at the bottom. They contradict with each other. Now, what is a phase contrast microscope do? There is a phase ring. They will add it. So somehow here, they add a phase ring. The phase ring will change the wavelength speed. They will let the wavelength speed either 1/4 wavelengths ahead of time or backwards. Ahead or backwards. There's 2. So once this happens, what we will do, this is no longer contradicting with each other. This maybe goes here. Okay, this maybe goes here, then goes here, goes here. So instead of you have these 2 showed up here, you have this guy and that guy. Then somehow you can see something. So that's a very basic knowledge behind the phase contrast microscope, because the phase ring, the speed of the wavelength is changed. So underneath the microscope, you could see something. And this is an example. Why? Before people having in a transmission electron microscope or laser confocal microscope. They want to somehow to know the internal structure, especially you can use those yeast and the molds. For example, Saccharomyces cerevisiae. This is the one you did the observation in our lab 1 practice microscope use. It's a beer brewing yeast. What you find? You find it looks like this. It's pretty boring. It's dark. And how about if you, under this phase contrast microscope? It looks like beautiful. You can see internal structure is very clear. That's the middle one, because the phase ring is changed the wavelengths, you can see the internal structure. And the last one is dark field microscope. It's not necessary to do it, but looks okay. So, what is a phase contrast microscope used for? To see internal structure of some microorganism, especially yeast, because we don't have to do staining. You can just watch it. Okay, that's a phase contrast microscope. Okay, fluorescence microscope. This is one we will be also briefly introduced to you. Fluorescence microscope, relatively a little bit expensive. If you say a traditional light field microscope is about $2,000, fluorescence microscope maybe like $5,000-ish to $10,000. So what's the difference? The light energy. This is need to use short wavelengths of light. So a good example will be blue light or UV light. Now remember, this is a good thing. Is that right? Use shorter wavelengths, the magnification will be increased. This is the first thing. Blue light, UV light. Second, this needs to do a special dye. These dye could be staining the genomics, which is DNA. That's called fluorochrome. And there is a different commercial kit. You can do it. The one used widely is the table at the second is called Davy stain. Okay? It's called Davy staining. The Davy staining called staining the DNA of a bacteria. So you need using a special dye, which is a commercial kit. That's relatively expensive, about a couple of $100. And you're staining it following the procedure. So you under this fluorescence microscope, you can do the observation. Now, what is the good thing for that? Because it stains DNA, so you know whether it's a dead cell or it's a live cell. If the dead cell, it is red color. Live cell, it is green color. Don't know whether I have a green color here. It is green color. Okay, just use a blue one as example. It's green color. So the good thing is that we can differentiate live and dead cell. Especially as in the food industry, if we do some food microbiology studies and using antimicrobials, we can see the bacteria, whether it's been injured, whether it's been dead. Then you using the Davy stain, using fluorescence microscope will give you a very good idea about that. And this is something, an example. Okay, when you see here, the red one is a dead cell. The blue one is a survived cell. This yellow one, it's most likely it is a little bit like injured cell. And the last one here, this is somehow is a yeast. Okay, it's obviously it's a green color. It's a live cell. Okay. Laser confocal microscope. This is something we want to talk about. Laser confocal microscope. We'd already talked about the laser confocal. Where is the energy resource? Is the laser. This laser, we call it argon laser. It's a commercial company called ZES. It's coming from Germany. Originally have a satellite branch in the United States. It's ZES company, the argon laser. I can show you the name. ZES micro image INC. That is the company have these tools, confocal microscope. Okay, use the argon laser. What's a good thing for this one? This is connected to the computer. It's a computer programming. You can see 3D images. Now, why you see 3D images is important because this is testing a special bacteria. It's called a biofilm, which is a matrix of bacteria community. It's not a single cell. In the lab, we have a bacteria grow in the broth. That's we call vegetative cell. Okay, so very simple. If I have this bacteria culture, I have a bacteria grow there. This is called the vegetative cell. You can easily understand it's a normal bacteria. If the bacteria growing on a bench, like this is called a biofilm. And we sometimes want to see the biofilm structure. That's why we're using laser confocal microscope. Now, why the biofilm will be forming? This is people failed the cleaning and the sanitation practices. So for example, I'm in a meat plant. There is a generic E. coli could be there. I'm processing the meat. Okay, I ground it, I packaged, I reconstructed and make a beef sticks. At the end of the day, this bench, I should have using chlorine to clean it, use water to spray it, and I didn't do it. So what happened? The bacteria will accumulate on the surface. And the more and the more they accumulated. It's like a group, like a matrix. And that will give you harmful results. The reason is those biofilm resistant to sanitizer. Most of the sanitizers. So for example, the vegetative cell, if I'm using chlorine, I only need 50 parts per million. Can kill it. If it's biofilm, even sometimes I use more than 10,000 ppm chlorine. It still failed. It's still not going to clean everything. That is the reason the sanitation standard operation procedure, the daily cleaning and the sanitation is very important in the food processing. That's a biofilm. But in the research area, we want to see the structure of the biofilm. We see the 3D images, so we're using laser confocal microscope. I did some of the research a long time ago by myself. This is almost like a decade ago when I was a postdoc working in USDA ARS, Agricultural Research Service in Beltsville, Maryland, not far away from here, about 3 hours. We didn't using 3D images, but we connected it to the color spectrometer. So this is some of my own research. So the story is that we do the bacterial growth on the stainless steel coupon. Okay, on the surface. And we stand with David stain. So you see these live cells. And the color spectrometer on the right side is following the green color. Then we treated them, washed with distilled water, water only. What do you see? Some red cells showed up, which means the cell started to die. And the cell is salmonella and the pseudomonas are mixed. And then you see the color spectrometer, some of them are red, some of them are green. And then we're using chlorine. We're using chlorine to do the sanitizing. You see, most of them will become red, a little bit of green. And the color spectrometer, you see, it's more isolated. And the last one is that we think the chlorine is not good enough, so we need to add surfactants. So we add a polypropylene glycan as a surfactants. And we think it will increase the decontamination impacts. And you can see majority of them become brownish color. It is injured cells. I have 2 live cells. So just want to let you know, laser confocal microscope can do the 3D images for biofilm, but also could connect to the color spectrometer. So it is a good combination for 3D images and fluorescence microscope as a dye. If we using the dye, we could know the differentiation between red cell and dead cell, live cell and dead cell, and we also could see the 3D images. So that's some good thing for that. Okay. Smear preparation. When we finish this one, we're going to end up here. Okay. This is exactly what we're going to do today in the lab. The smear preparation is a simple step, and the 930 lab already did. Then the next follow-up lab, we're going to do it. So, how we do it? You have a glass slide. You need to make a very thin film, which is called specimen. So put 1 drop of the water, then you add the bacteria, make a smear. The smear, first of all, need to do the air dry. Air dry about 3 to 5 minutes. If you didn't do the air dry, what happens? Underneath the microscope, you're going to see the color, it looks like this. I tell you, lots of legs. I call these are legs. Very fuzzy. So you have to do is an air dry. After air dry, we put the glass slides on the Bunsen burner back and forth. We do the heat fixing because we will try to kill the enzymes, let them stick on the surface. Then we're going to add a dye. So what kind of the dye we can add? The purple one here we call crystal violet. And the pink one is saffron. And there is sometimes the green one, we call it a malachite green. The blue one, we call it a methylene blue. So there's a different type of the dye. So we added the dye, then we dried it out, then underneath the microscope. And underneath the microscope, what we could see is the cell shape, is a morphology and also the arrangement. So there's a question for you. Why we can do a simple stain? And I already mentioned in my first lab, because the bacteria, when they grow in the broth or on the slants, it is negatively charged. And those dye we use in the lab, the crystal violet and the saffron, it is positively charged. And the positive and negative charge, they could be combined and stick together very well. Therefore, we could see the morphology and arrangement of the bacteria. That's what the basic dye looks like. In other words, there is some of other dye, which is like a nigrosamine Indian ink. They are, instead of positively charged, they are negatively charged. So they are staying in the background. And then the sample will be showed up. So that's called a negative stain. So negative stain looks like that. Okay? This is more we're going to talk about next week Tuesday. So next week Tuesday, we will talk about these gram stain. We'll spend lots of energy to talk about that. Okay?